Hey guys, how's it going? Um, First of all, sorry about my appearance. I just got out of the shower. Second of all, I want to apologize about the extremely late video because I know this lab report is due tomorrow. First of all, I want you to know there is nothing to worry about. From what I've seen of the first lab report you guys wrote for experiment 2, you guys did exceptionally well. There was a lot that you guys need to work on, but I was extremely surprised with how extraordinarily well all of you did collectively. So be proud of yourselves. That's great. Nothing too much to warn you or talk to you about there because I think I already addressed that in some previous videos. I'm going to make this a short video today if I can, as short as I can. First of all, so we have lab report coming up. That's due tomorrow. And again, I am sorry there was a mix-up with the due dates and I didn't quite get the memo that it was going to come up so soon and that the previous experiment was due simultaneously with experiment 3 and 4. So anyhow, today we're talking about partition coefficient. So I'm going to walk you guys through some of the calculations and then I'm going to give you guys some examples of what they want you to review. And I'm going to make this short just because we have a lot to review as far as stereochemistry is concerned. Because from what I've heard, a little birdie told me you guys have exam on October 23rd, I think. It's like we have about 2 weeks, I think, to prep you guys for this exam. And if stereochemistry is on it, everything you've learned up till now will be the least of your worries. That'll be easy. I need you guys to make sure you know this stuff and it's in your memory bank because stereochemistry is only a singular part of your exam. It's only like, if you know it, it's a small percentage or portion of what your exam is going to be on, but it's by far the hardest by a lot to understand and grasp. For some, it's extremely easy. So I don't want to threaten anyone or dawn anyone or anything. Maybe for all of you, it'll be extremely easy. Hopefully it is. Hopefully I help you guys enough. But for some and most usually, it's hard to grasp because you have to be able to picture, break down, and manipulate objects in a 3D and 4-dimensional plane of view in your mind, kind of. It takes a lot of mental power, or it doesn't. Maybe if you're real creative or you can think outside the box. Hopefully I can explain it in a way. Everyone's capable of this. Everybody, all of you are. All of you are capable of getting hundreds on this exam and doing extraordinarily well. It just depends on how well I elicit these topics to you. So it's on me. It's how well can I teach you guys these topics, and Zach, Professor Poulos. So more of that will come next week. And I apologize, I said this was going to be short and I just took up a lot of time trying to stress how important this upcoming exam is going to be and how important studying is going to be, especially with stereochem, because that's so hard to grasp for a lot of people, stereochemistry. But now we can begin. Partition coefficient. So I'm going to share my screen with you guys, start there. Alrighty. So first off, we're looking at the rubric here, partition coefficient. So there are a few things that are just pretty generic on here that I would like to address. First of all, it's the 4-part or 5-part actually in this case lab report that we're used to. So you have an abstract where you have your statement of the purpose. Why are we doing it? I'm going to address that in the chemistry in a moment, and you'll be able to explain it in better detail later. Also, since it's at the beginning of this video, beginning-ish, I would like to address, I know that some of my students have already submitted their lab reports because I am posting this video so late. That is fine. I know that you use the exact numbers from the video to do your calculations. I will accept that from those students. Keep in mind I can see when you have already posted, and I am recording this at 8:38 p.m. on Saturday night. And again, I am sorry for the lateness. But I'll be probably posting this in about an hour or two. For those students, that is okay. Otherwise, I have some numbers here that are slightly different that I will provide just to make sure you guys all know the calculation. Students that did present their reports early, I will be in touch with them if I haven't already, and most of them or all of them I already have been to make sure that, Zoom call, check in, make sure they understand chemistry and other stuff, etc. But back to this. So not to worry if you've already put it in and you didn't, use the numbers I'm about to give you for your calculation, because I have or I'm about to speak to you, so it's okay. But procedure overview, like I said, 3 sentences, abstract, should be easy, statement of results. So basically, 1, 2, 3 sentences. The first one, why you're doing it. The second one, how you did it. The third one, what were the results? What was the comparison partition coefficient of your benzoic acid in your water to methylene chloride to your sodium bicarb solution to methylene chloride? What were the results? Quick, 3, 4, 5 sentences, very quick. Procedure, you can copy and paste it, like I said, doesn't matter. Reactions, we do want you to draw out the reactions. Usually we request the students use ChemDraw. Here I have it uploaded again. If you don't have ChemDraw downloaded, then honestly, these reactions are extremely simple and generic. If you Google, and I even have an example here actually that I'm going to bring up again later, but I'll show you now just for this take. No, maybe I don't know where it is. Anyhow, if you Google these reactions, these exact ones, they're pretty generic, so you're able to find them. If you're able to, please, please, please include them in your reports. It'll do you a lot of good, trust me. I'll see that as a huge bonus. I will enjoy that. Make sure that you elicit the reactions. Actually, the reactions themselves here, I have Blackboard open, or the notebook open. The reactions themselves, the acid-base reactions in general, are right here. Right on Blackboard. I pulled this out of the notebook pages that were posted for week 6, experiment 6, partition coefficient. If you want, you can screenshot this and crop the photo, or if you are more equipped, you have a different computer that has this data, you can right-click and save the image itself, but since it's a ChemDraw file, I think it might be easier for everyone to screenshot and crop the photo and include it, but it would help. And also, you know, don't just include it, because I know it'll come from the notebook. If you include this, explain it enough in so many words that I know that you know what's going on, because really there's only a few words here, like, you know, labels, the reaction label, letters for the, you know, atomic symbols, etc. Put in so many words that you know what's going on, kind of like a dialogue for the image if you're going to go that route. Anyways, data and calculations, I will get to that in a moment, actually right now, because I have this open. So, partition coefficient. We're kind of far into the video in my relative standards, because I really wanted this to be like a 10 to 15 minute video, but clearly it's not going to be. Partition coefficient calculations. First off, I spoke to you previously about equilibrium in past videos. I realized that I screwed up and posted the experiment 5 review before, or after, about 18 hours after the actual due date of the experiment 5, because there was a mix up with the due dates, and I didn't realize that it was that same day as the 3 and 4, and I apologize. So I'll just say it again. We know that organic dissolves inorganic. So if you have an organic solid compound, it will dissolve an organic solvent. And we know that inorganic or ionic solutions like salts, etc., with metals and whatnot, cations and anions, ionic bonds and whatnot, strong dipole bonds, or dipole ion bonds and ion-ion bonds, they dissolve in aqueous solutions. So inorganic dissolves in aqueous, inorganic, and organic dissolves in organic. But every single compound has, to some extent, an equilibrium. So equilibrium means that even salts, sodium chloride, that we know is an ion-ion bond, and it dissolves in water. So it shouldn't dissolve in organic solvents, correct? So if we combine 2 immiscible solvents like water and methylene chloride, okay, like for your, kind of like your lab, and we have something like sodium chloride, for example, and in your lab you use benzoic acid. But for this example, we just have water, methylene chloride, and you know, methylene chloride is going to be on the bottom layer because it's more dense than water, and salt. So we know the salts, the majority of it's going to be in the water. But because of equilibrium, nothing is absolutely perfect. Even things that are almost infinitely small in concentration in the organic phase, when they're actually salts, they still exist there. So even if it's a point, if it's 1 × 10⁻⁸ even. That's just an arbitrary number I came up with, but it's one that accurately describes exactly the range of equilibrium you can have. Because you can have something that is extremely insoluble in water, and even then, in a partition where you have something water and another organic solvent that it's miscible in, to some extent, to even the smallest extent, you'll have some of that atomically in the aqueous region, and that is the partition coefficient. So basically, it's a ratio of how soluble something is in organic. Because if you have two organic solids and they both dissolve in organic solvents, one of them dissolves more readily than the other. How do you decide which? You compare them by looking at the ratio of how it dissolves in the organic to the aqueous. By putting them in an aqueous organic solution, shaking them up, letting them settle, solvate settle, like go into solution or come out on their separate sides, equilibrate, and then taking off the organic layer, okay, removing all water whatsoever, which is what you do in your experiment, and then dissolving the organic layer or evaporating it, and then measuring the mass of how much is in the organic layer. And then by measuring that mass, you can determine from the original mass instituted or incorporated into the system how much mass is in your aqueous layer. So this is what the partition coefficient is, and this is what your experiment is. Your experiment is essentially, you take benzoic acid, which we know is organic and dissolves readily, and is a solid, and dissolves readily in the methylene chloride. So when it's a methylene chloride and water solution, the methylene chloride will be on the bottom because it's more dense, the water's on top. Benzoic acid is going to primarily be in the methylene chloride. Because of equilibrium, to some extent, it'll be in the aqueous, but a very, very small amount, all right? And we use specifically methylene chloride, water, and benzoic acid for this example so that there is a difference of more than 1% so that we can demonstrate properly to you how equilibrium works. But even things that are extremely soluble have equilibrium, so they'll end up in things that seemingly are less soluble, even if they come in contact. That's why when you have something extremely pure, you want to handle it with very care, keep it in a very contained environment and under very inert conditions, etc. But getting back to what I was saying, we have the benzoic acid. So in the procedure, we include 50 milligrams and 600 microliters of the water to 600 microliters of methylene chloride, shake it up, and we end up with an abundance of our benzoic acid at the end of what I just said, because we have to extract methylene chloride, the bottom layer. All right, and we remove the water by adding an anhydrous agent, okay, a water soaking up agent, something that takes up a lot of water. So 1 molecule of sodium sulfate can take up about 7 molecules of water or 10 molecules of water. I'm forgetting right now, but it's 7 or 10 sodium sulfate. So it absorbs it all chemically, and then we filter it through, the column with the cotton. So we know that we get all of the solid, etc., and it chemically is bonded to the water. So we chemically remove the water, rinse the solid with the more methylene chloride, evaporate it, and measure the mass. And then that's how you get your calculation for your partition coefficient. I'll scroll to the bottom real quick, and then I'll scroll back up to describe that. So the original mass, supposedly you entered 50 milligrams. I want you to explain the fact that, how equilibrium works. Even something that's incredibly soluble in organic solutions, to some extent, is still going to be soluble in aqueous solutions. That's the chemistry involved in the discussion. Remember, the discussion is the most important part. I know you're going to get your calculations right, because I know you guys watched the video, and whether or not you use the numbers from the video or from my video here in my email, I will be able to analyze them. And for the most part, you guys will do that well, whether or not you just copy them from the video or not. The chemistry explained, the concepts is what I want to see. So anyhow, we'll go through this. I didn't explain the sodium bicarbonate, so I guess I'll do that real quick before we go through the calculations actually. So same experiment for part B. Now I'm addressing part B, and I'll do it extremely quickly, or as quickly as I can. Originally, we're incorporating benzoic acid and methylene chloride and water solution. Now we're incorporating benzoic acid into a methylene chloride water with sodium bicarbonate solution. So, backing up, sodium bicarbonate is a solid, all right? It's better known as baking soda, etc. It's a white solid. We saturate the water with it, and it dissolves in water readily because, as we know, it has an ion dipole bond between the bicarbonate. That's why we call it a bicarbonate instead of bicarbonic acid or carbonic acid, because there's no H there. It's just an O minus, and it bonds to the Na plus. So it's sodium Na plus bicarbonate O minus. So that goes into the water until it can't go in anymore. We test that by adding sodium bicarbonate more and more and more to the water and shaking it up until it stops dissolving. Once a tiny bit of sodium bicarbonate starts to collect on the bottom of the bottle, we know it's super saturated. So we just call it a saturated solution. So we know there's enough sodium bicarbonate. So we have that methylene chloride now. Now they're still aqueous and organic, so they're going to stay separated, partition. Because what do we know about the word partition definition? It used to be used in hospitals by nurses so that when patients were sick from the flu, in order to separate them to keep germs apart. We're in a pandemic now, this might be relevant. They kept up a partition between the beds to make sure that people were, when they were coughing, no one's bringing germs, etc. So partition coefficient, it's the partition between the aqueous and the organic layer, just like the partition between the beds in a hospital back in the day. So we want to know the ratio of how much a solid compound dissolves in one side of the partition relative to the other, even though we know it's supposed to dissolve relatively almost all the way here. To some extent, even insignificantly, it dissolves up here, and we got to measure that ratio, and that's the partition coefficient. So in the sodium bicarbonate, for example, when you add the benzoic acid, the pKa, and keep in mind, pKa describes how acidic a compound is. So the less of a number of pKa the smaller the pKa is, and it goes into the negative numbers, that describes a more acidic compound. So for this example, the benzoic acid is 4.19, and the sodium bicarbonate water solution is, and NO just says sodium bicarbonate, but it means aqueous sodium bicarbonate solution, okay? Just to be clear. And I remember, just because I remember when I was taking organic chemistry, that was totally unclear when I was reading reactions. But anyways, the pK is 10.32. That's relatively high. That relatively means base. And sodium bicarbonate is a relatively strong base. It can't burn you, but in like weak chemical terms, it's stronger than acetic, or strongish around acetic acid is to acids. So sodium bicarbonate in this circumstance still has a higher pK. So in this case, it acts as the base. And a base takes a proton, an acid donates a proton, remember. So in this circumstance, when you have benzoic acid and sodium bicarbonate, if you look at my mouse, the benzoic acid and the sodium bicarbonate together, the sodium bicarbonate will take a proton from the benzoic acid, become carbonic acid, and sodium benzoate. And here's where it gets interesting. Now, if you can look where my mouse is, the KEQ says it's greater than 10.217. And that number is the exact KEQ if you calculate benzoic acid plus sodium bicarbonate become this reaction. The KEQ for the reaction if you calculate it, which is actually the 10 raised to the pK of the conjugate acid minus the pK of the acid. So the difference between the conjugate acid and the acid. So how readily the acid dissociates, basically, 10 raised to that power. But this is where it gets interesting. If you look where my mouse is on the second reaction here, carbonic acid, now this is where it gets relative, relative to your real life. That's found in all soda. So that's how you carbonate soda. So if you have a soda stream or something, it's essentially, so those canisters are filled with gas. However, when they make soda, they use carbonic acid and it's dissolved into the fluid, the water, and it's mostly water. And the thing is, carbonic acid is so unstable because when it breaks down, if you look at its chemical structure, it's HO, that line down connects to a carbon, and then the double lines to an oxygen, and the single line to an OH. If you look, it just CO2, so the C is the middle vertice, and then two O's, CO2, and then OH, and then if that OH bonds to the O, it bonds to the H above on the top of the vertice, then it forms H2O. And that's exactly what happens. because water and CO2 are so much more abundant and so much more stable than carbonic acid. So as soon as carbonic acid forms, it readily breaks down into CO2 and water. And that's why your soda drink is like, it's filled with pressure because there's so much carbonic acid. It readily is breaking down to CO2 and water. So that's a lot of CO2 up here in this area where it's compressed, all right? And that's water going in. So that's why when you leave it open for a while, a lot of CO2 is generated, leaves the bottle, and as a result, water is a byproduct that gets added to your soda. So a flat soda isn't just non-fizzy and bubbly, it's also watered down because as a result of CO2 being generated, water is also generated. And that is exactly, if you look at my mouse, what we see here. So even though the KEQ is 10.217 and it might suggest that the reaction might go a certain direction, because carbonic acid has an incredibly strong, so strong that it significantly overpowers this KEQ of its own, it forms water and CO2, this gas. So it pushes the equilibrium very strongly to the right side, if you look at my hand and my mouse. So it strongly forms a sodium benzoate in the carbonic acid. And that's why you see an incredible difference in the partition coefficient between the regular water and the methylene chloride and the sodium bicarbonate water and the methylene chloride. Because benzoic acid prefers to be in the methylene chloride because it's organic. But once you add sodium bicarbonate to the mix, that base, all of a sudden, your benzoic acid is going to want to head over there. And as soon as that carbonic acid forms, it's going to break down, form CO2, and now it's gone. The CO2 has turned into gas and it has left the system. Ladies and gentlemen, CO2 has left the system. You can't get it back. It's not going back into that reaction. You have a watered down reaction and you're not getting that CO2 back. So now you're going to get an abundance of your benzoic acid, your previously benzoic acid, now sodium benzoate trapped in your aqueous solution. So one of your partition coefficients should be essentially opposite to the other. So that explains all the acid-base chemistry and whatnot. So now I'm going to very quickly, or as quickly as I can, because oh my gosh, it's been quite a while, over an hour. I am going to go through each of these bonds because this is all relevant information also for your exam, guys. Not just your report. So keep that in mind, and please, for your own sake, address this video as much as you can before the 23rd. And I'll be posting again in response to StereoChem. And I'm going to go through each of these reactions because they told you guys to review, and I want to make sure you guys have a clear understanding because some of these concepts are confusing. So first of all, ion dipole. So ionic forces, we know, are inorganic forces. So here I have an example from Khan Academy video, and I didn't check, but I just recognized the penmanship because back when I was 15, I actually used to watch these videos to help me do some classes in freshman year of high school. They've been great even since, and they work even now in college. They're amazing. But anyways, here we have an example of sodium ion and a zinc ion. And here is an HH, a hydrogen dipole, diatomic bond. So usually they share the electrons, they have the same electronegativity, so the electrons just float back and forth. But something very complex that we cannot address at all in depth right now called quantum mechanics and Heisenberg's uncertainty principle. Some of you have seen Breaking Bad, you've heard of Heisenberg. Heisenberg's uncertainty principle tells us you can never know the exact location and velocity, vector quantity of an electron and its exact position. So even though the electrons are shared, they have electron orbitals, and you can never pinpoint an exact location of the electron. You just know it's always somewhere, and at the same time, at all times, within that orbital. So in all places at once, and also nowhere at once. So the positive and the negative are happening. I'm trying to explain electron orbitals when I should just be explaining ion dipole, sorry. But anyways, in an HH bond, as you see right here, the electrons are shared, but when it comes in contact with something with a strong electric charge, like +2 zinc, it draws the electrons to one side of the molecule, whichever side is closer to the zinc, and that's what induces an dipole. or dipole. And that's more of an induced dipole, which we'll talk about more later. A regular dipole, maybe the OH, the water molecule. So we know O is a higher electronegativity, so it is has a higher attraction to electrons than hydrogen. Hydrogen has one of the lowest electronegativities, even though it's at the top of the periodic table. It is the smallest element, the smallest atomic radius. So even though they share electrons, they're pretty much hogged by the oxygen. So there is a dipole there, partial negative, partial positive charge. And so here we have an ion of sodium with a positive charge, and here we have a partial negative and a partial positive on this water molecule. So they form an ion dipole. That's a good example of an ion dipole. I should have started there. And here's more of an induced ion dipole. And I'm going to give you another example apparently in a minute, because I didn't realize that that was a perfect example of an ion dipole in that diagram. But here I want to express van der Waals, because there was no good diagram that I could find anywhere on the internet for van der Waals, so I'm just going to have to explain it now. So with van der Waals, this is an extremely non-polar compound. So here I just brought up a picture of butane. Four carbons bonded together with their hydrogens around them. So we have a CH3 with CH2, CH2, and CH3. So 4 carbons and 2 methylenes and 2 external carbons. And here I drew their electron orbitals and where their hydrogens bud out. Or here I have an image where their electron orbitals are displayed. So, like I said previously, we cannot determine, because of Heisenberg's uncertainty principle and because of quantum mechanics, we cannot determine the exact location of electrons, but we do know that they like to aggregate or clump together, form together, bond together, like clump up together into little masses if they're attracted to a location. So even though they're pretty much evenly distributed, they're pretty much randomly bouncing around. And occasionally they accidentally, by some coincidence, because coincidences do exist, even though they're extremely, they are plausible and they are possible, even though they're extremely improbable. They do exist, and occasionally they happen. So one butane next to another butane might accidentally, their hydrogens or their electrons aggregate to one end of the orbital that's shown here if you look at my mouse. And it might happen at the same time to coincide with another orbital of butane that happens at the same time for electrons to come together at that end of the orbital. And they will repel, that's a force. Or the opposite, maybe they're attracted to the exact opposite side orbital, the white end. And now there's an electron, now there's a negative side, so there's a dipole. All the electrons are on this side. If you look at my mouse, sorry for raising my hand. If you look at my mouse on the image here, all the electrons are on this side. Maybe your butane that's up here, all the electrons are here at the bottom. Now you have a positive charge here because you have all the negative charge bonded or crowded together over here just by chance. This is all just by chance, happenstance. And they will interact. So that's why they're incredibly weak, because it only occurs by chance and it's incredibly improbable, but possible and plausible circumstance. And we do see it in nature all the time. Now for the next example, and this is all for your exam, by the way, but feel free to mention this on your report because it's great practice, and don't feel bad if you copy and paste it to some of your short response answers on the exam, because I know Poulos likes to give short response answers, and intent pre-writing them in Word and copy and pasting some very relevant facts in will help you a lot, like personally written, because everything gets scanned through our algorithm and our software. And if it's ever been written or reported or anywhere on the internet, it'll find it and we'll know. And most of you guys are very honest, and I'm so proud of you guys, and I love you guys for that. But unfortunately, we do catch occasional people that, either, and most of the time, sometimes it's like a circumstance, like a family thing, they couldn't get around. So they decided to take an easier route out and have someone else write their paper, copy and paste something that's previously written. But we talk to the students, and the most part it works out. But most of you guys do exceptionally well. I haven't had any issue with any of my students, by the way. I know students from other sections are watching this video, so I just wanted to say that. But for the most part, all of you are doing extraordinarily well, as far as I'm concerned, as far as I know. I'm very proud of all of you. I just wanted to point that out because, no man gets left behind. But anyways, Here's what I was going to use for induced dipole. So another kind of example, here's a partial positive, partial negative charge. So this is a covalent bond. They share their electrons. Chlorine isn't the most electronegative element, but it is over there. It's a halogen, and electronegativity goes in the up to the right direction on the periodic table. So towards fluorine. Fluorine's the most electronegative because we don't count the noble gases. Remember that. Remember that, guys. We don't count the noble gases. So for the most part, they do share. But if you have them all in a very concentrated amount, if you have concentrated hydrochloric acid, you can't have certain bonds between them. So they can be a little cohesive. And that's just cohesive means something is attractive to something of itself. Adhesive is something is attractive to anything else, whether it's not itself. Like if water was adhesive, it would be attractive to anything, metal, plastic, wood. But it's cohesive, so instead it attracts to water, which is why trees are able to grow so tall, because water's cohesive ability applies for capillary action, so it can climb up the inside of its roots. That's relevant, but a little fact, a little fun. So moving on, to help you with the exam. Induced dipole. Oh, here's a good example of an induced dipole. So we have another water molecule, and we have a molecule of oxygen. So oxygen, we know we breathe, it's a gas, and water, and standard temperature and pressure is a liquid. So they actually can form bonds. So the ocean, water to oxygen in the atmosphere, they can actually form bonds to one another, because even though oxygen and oxygen share a bond because of Brinkelhoff, BRINCLHOF, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those are all the all the elements that are found in nature that only occur in their natural state as diatomic, meaning that they're bonded with another atom of themselves. So you only find, for example, fluorine F2, hydrogen H2, oxygen O2, chlorine Cl2, Brinkelhoff. That's what we named it. But anyways, Brinkelhoff, O2. It's one of the Brinkelhoff, diatomic, so it's oxygen, it's a gas at natural state. But when it gets close to water, because water is a dipole, it can form an induced dipole. So the electrons are attracted more to one of the oxygens, so it's attracted more to the negative, opposite. The electrons are pushed closer to the opposite oxygen. So this oxygen becomes slightly more positive and can be attracted to the oxygen found in water. So you get a slight surface tension. That's actually what surface tension is. When you have certain gases in the atmosphere that react with solvents or liquids at room temperature and standard temperature and pressure, and how well they bond and what their relative pressure directly above the liquid is. That's called Henry's law, but that's completely irrelevant. And, well, it's analytical chemistry. It's kind of basic stuff. It's going to last year. Hopefully you guys know. But otherwise, if it comes up again, I'll bring it up. Or if you guys have questions, ask me. H bonds, hydrogen bonds. So here's an easy example. You guys will probably see this all the time on the exam. Water molecules. So like I said before, oxygen is highly electronegative. Water is significantly less electronegative. So we form a dipole. So we have a partial negative charge to a partial positive charge. And so when you have multiple water atoms, molecules, goodness, I can't believe I said that. Water molecules together, like a cup of water, they will form this kind of bond. So an H to the O bond. And that's pretty common. You'll see that all the time in chemistry. H bonds can form between hydrogen and oxygen, and hydrogen and nitrogen, and in rarer cases, hydrogen and sulfur. And even rarer cases, other elements, but I doubt you'll ever come in contact with any of those on an exam. But hydrogen to oxygen, hydrogen to nitrogen, hydrogen to sulfur, H bonds, but mostly oxygen and nitrogen. All right. Now, cation, ion. All right. So, cation, pi electrons. So disregard this right side because these are a bunch of amino acids, and this pertains to some paper a drug that elicits a certain protein and prevents neurodegenerative disease. What I want to address is this image on the left. So if you look at my mouse, we have an ion of sodium, so an Na+. And now here we have a benzene. And I know you guys have seen the circle inside of the hexagon and the dash, space, dash, space, dash, space. So every other line has a double line. You've seen that before. They're the same thing. Same thing. They're both called benzene. B-E-N-Z-E-N-E. I'm sure I hope you guys already know that, but I just want to make that clear. So anyways, this is called delocalization. Now, if you've been unfortunate enough to listen up till this point, I'm going to share an extreme secret with you that brought me to a new level in my intuition in chemistry. Because I did finish top of my class in chemistry. That's not a brag, but I just want all of you to do extraordinarily well because there's a lot to it that's extraordinarily important, and I would appreciate, all of you to appreciate it as much as I do. Because I was lucky enough to have such an amazing mentor. It was mostly luck. It was almost all luck, 99% luck. But Dr. Shia described it. Delocalization versus localization. So each of these single lines, and this is mostly for your exam. I'm sorry I'm making it so much longer than I said I would. Each of these single lines represents a sigma bond. Each of the double lines you would see otherwise separated by one represents a pi bond. Okay, sigma and pi. That's a second pair of electrons to make the bond stronger. Now, when you see a regular double bond, that's also pi electrons, but only if they're one bond away from another set of pi electrons, so another double bond, can we consider them conjugated or delocalized to a certain extent. So if you have pi electrons on a sigma bond, and then a regular sigma bond or single, so a single and a double, and then a single, sigma and a pi, and a sigma. And then a sigma, and then another pi right here. Since they're one apart from one another, we call them conjugated or delocalized to a certain extent. All right? Now, when you have a hexagon, they can be perfectly separated by one bond each and also bound in a circular ring. So this creates a very, very unique and extremely stable orbital, delocalized, conjugated orbital within the hexagon, the benzene, B-E-N-Z-E-N-E ring, where the electrons can travel freely. So even though sometimes we draw it as line, space, line, space, line, space, and sometimes we draw it as a circle, always consider the electrons are constantly moving randomly throughout the benzene ring. This is just carbons and hydrogens. It's completely nonpolar. It's basically van der Waals interactions, but they float as freely as they want, randomly, because of Heisenberg's uncertainty principle. They can be concentrated or deep or extremely separated and spread out as much as they want, one direction or the other. Extremely concentrated in one area or extremely spread out. It's completely random because of quantum mechanics and Heisenberg's uncertainty principle. But we do know they're delocalized or conjugated or spread out. So if you just have, but if you have a chain of carbons and you have a double bond, a single bond, and another double bond, they can only travel between those two. All right? And only if there's something extremely electronegative or an ion pulling them that way. The special part about pi stacking and cation ion or pi cation reactions are that since the electrons are delocalized, the ion can focus itself directly above a planar, completely flat organic molecule like this. And because the electrons are delocalized, they can perfectly situate themselves, spread out perfectly as close to the center of the hexagon as possible without breaking their bonds to the nuclei of the carbon on the outside, and perfectly spread out to stabilize the cation in position. So you can stabilize sodium plus or magnesium 2 plus or zinc 2 plus directly over a benzene ring. And then lastly, that just brings us to pi stacking. Since I already explained benzene and pi stacking, this will be quick. You have two benzene rings. I told you before, van der Waals occasionally by coincidence, even though it's extremely improbable, it is plausible and possible. They can stack each other. A strong example, which I didn't necessarily want to show you, but plays a strong role, which I will tell you, and it's huge because it's kind of the biggest thing happening right now in science between physics, chemistry, and biology, between genetics, cold fusion, etc., is battery technology and energy storage. And they use graphene as kind of like a god molecule to store energy, to store ions of high energy potential in batteries for energy storage. Because even though we can collect energy from the sun and solar light, we need something that can store it indefinitely for a crazy amount of time. And graphene is a completely carbon, if you've heard of like charcoal or coal or graphite in your pencil, it's all just carbon. And that's what graphene and lithium ion batteries and the newer batteries that are about to come out, sodium solid state glass batteries. They're also carbon, and they're also hexagonal 6 carbon structures similar to benzene, and they participate in pi stacking as well. So that's kind of a relational example to real life. But as far as the report is concerned, just include the chemistry for the partition coefficient. I went over the calculations previously. I mean, you guys know the Ka is equal to the product of the concentration of the conjugate base times the conjugate acid divided by the concentration of the acid. So, and then we know that the pKa, which is an explanation of how acidic something is, or how willing something is to donate a proton, it's equal to the negative log of the Ka, and I just explained Ka. And we know the pH is equal to the negative log of the concentration of the conjugate acid. It's just in this example, the benzoic acid donating its proton to the water. So the conjugate acid, the base in this example is the water, and it becomes the conjugate acid, the hydronium ion. So the pH would be the negative log of the log base 10 of the concentration of the hydronium ion. The way we find out the concentration the acidic versus the organic is we just, we isolate the organic, like I said, we eliminate all the water, we eliminate all the organic solvents, and we mass it out with the tare weight, and then from that we can subtract from the original mass of our benzoic acid, and then do the calculation. I hope you can grasp by now that this video is more geared towards helping you understand the concepts that are for your upcoming exam test, and less so for the report. I grade your report. I give you your points for your report. If someone's not doing well in lab, I address that. I email them, I call them, we talk, I share what I know, I make sure they understand the concepts, and then more importantly, I make sure they're ready for the test. So nobody fails my class, because when you're failing, I just freaking call you. And I, talk to you, see what's going on, explain some stuff, and make sure you understand the topic, and we can do something about the grade. So don't worry about lab. My struggle is making sure you know what to do for the organic exam. Because usually before COVID, I would help grade those exams, and I could help curve them a bit with Dr. Kelly, because he was really head of organic. And as long as we could address it and meet with students and make sure they understood the topics, give them acceptable grades to make sure that organic wouldn't hold them back in the Form 2 program. Because the last thing we want is for any of you to drop out or fail because of organic chemistry. That would suck, and it happens to way too many people every year. It doesn't happen to many, but even one is way too many for me. So really, any question you have, click the exam. Anyhow, back to the last comments on this. I'm going to just go over the partition coefficient calculation. It's very simple. The original mass minus the recovered mass, and then you get the aqueous mass. Then we know that because of the calculations previously described in the procedure, which you can see above, which I talked about earlier. We have the mass in the organic layer divided by the mass in the aqueous layer gives us our ratio, the partition coefficient, and vice versa for the sodium bicarbonate. And I explained the chemistry previously, but that should tell you why it's so wildly different. Because we expect to see more of the benzoic acid go towards the aqueous side when there's sodium bicarbonate in solution as opposed to when there isn't. When it's just plain water, it prefers the organic layer. When there's sodium bicarbonate stuck in the water, the sodium bicarbonate drags the benzoic acid into it. It craves those protons. It's like, give me those freaking protons. As soon as it gets them, it forms carbonic acid. The carbonic acid turns into CO2 and water. All right, you're adding water to the solution. Great. The CO2 is gone. It turns into a gas. It bubbles away. Can't get that back. There's no equilibrium there. It's gone. It's in the wind now. It's a wild particle. CO2 is gone, and the benzoic acid is trapped as sodium benzoate in the aqueous layer when you have sodium bicarbonate solution of Part B. So that should help you explain the chemistry involved. Again, here are the numbers that Zach gave you: 67 milligrams, 57 and 56 original and recovered. That's for Part A, and then for Part B, 65 and 8. So just like I said, in the regular water, you expect a large recovery relative to what you put in for the organic layer. And when you add sodium bicarbonate, you expect a small recovery from the organic layer. So you reverse extrapolate how much you expect, 57 milligrams for this example, 65 minus 8, 57 in the aqueous. That's when you do your calculations, you get the Kp, partition coefficient of methylene chloride to water versus methylene chloride to water sodium bicarb solution for benzoic acid, Kp difference, the log P's. If you stuck around in the video this long and you haven't posted and you've held out, thank you very much. I appreciate it, your patience. I would like you to use these numbers: 63 milligrams original, 59 milligrams recovered for the water Part A, 68 milligrams original, 4 milligrams recovered sodium bicarb solution Part B. All right, bing, bang, boom. If you've already posted, don't worry. I will address that and keep that in mind. Otherwise, I expect to see the solutions to these answers, and I expect to see all the work. Good luck, and if you have any questions, give me a holler. I'm going to end with this little diagram from the video I posted with the lab. It's my thumbnail from the last video. So here, look at my mouse. Here's the carbonic acid that's forming. All right, so we have sodium bicarbonate originally. And now here's the hydrogen ion, the proton that it's getting from the benzoic acid. It grabs the benzoic acid and immediately forms carbonic acid. So I know this is a double-ended arrow, but it should be strongly favoring the carbonic acid, all right? The carbonic acid. Now, as soon as the carbonic acid forms, now it has this other reaction that occurs. Forms water and carbon dioxide, as I previously said. I know it's another double-ended arrow, but it should be strongly favoring towards the CO2 H2O. So if you follow my mouse, because I don't know what my camera is showing relative to that, to the direction my mouse is very fastly or quickly accelerating, that's the direction that the equilibrium is favored. So carbonic acid immediately breaks down into CO2 and water. You cannot reform it. Therefore, the sodium benzoate is trapped in the aqueous solution, and you get a completely opposite partition coefficient for Part B. I hope this helped, and I hope this helps with your exam. I'm sorry it was probably the longest, or definitely the longest video I ever recorded. Godspeed.